In this problem, we want to hold this windlass in static equilibrium, so we want to know, under these conditions, how hard do we have to pull, that force P, and what are the reactions going to be at the ball and socket joint at A. So let's find all the reactions at A, and that required force P if we're pulling completely in the x direction to maintain static equilibrium. So we'll start with the free body diagram. I will keep the given coordinate system, putting the origin at A, having my z-axis and my x-axis and my y-axis. Okay, so let's see, what object do we want to keep? So we need to have the reactions at A, which means we can't have the connector here in our object because we want to know what that does to the system that we're keeping. We're going to be applying this force P. We don't want that journal bearing. That's another thing we're looking at, is what are the reactions at that self-aligning journal bearing. So we can't have the bearing itself, so we need to include what the bearing does to the object that we keep. And in this case, we're also going to have the weight from the ball. We don't need the ball itself. Whether we keep it or not doesn't really matter, but we'll have the tension of 150 pounds that the ball is pulling down with. So really the object we want to keep is this structure here. I'll outline in green, a little bit tough to see, but I will recreate it here. So it's going to go along this direction. It's going to go in that negative z. It's going to go in that positive y direction. Right, so that's going to be the object we keep. Again, we're going to be able to now see the effects that the ball and socket at A and the journal bearing at B have on this, as well as the weight of that ball happening. Right, so let's start by looking at external forces impacting our system. So we're going to be seeing that applied force P happening. So that will get included. And that is going to be happening at, it doesn't have a name yet, so I will call it D for simplicity. That we are pulling it, and D is located at 0, 6, -1 feet. Then we're going to have our point B we'll get to. We have our point A already. And we also have an applied force over here where this tension is. So we want to be careful here because it's happening not through the center. It's going to happen 1.5 feet from the center. So this tension, or this force of 150 pounds, is offset a little bit. And I'm going to call that point C, and that will be at positive 0.5 to 0 feet. Right, so again, we want to be careful. It's not happening through the center of the shaft. It's happening on the outside of the shaft. It's happening on that external radius of 0.5 feet. So those are the external forces, the applied force P and the weight force of 150 pounds. So to continue modeling this, we need to know what's happening at the supports A and B. What does the ball and socket do to the object we kept? What does the journal bearing do to the object that we kept? So at point B, which it's at 0.40 feet, we are going to have here, it's a journal bearing. Journal bearings allow translation along the axis of the shaft. So this shaft can move through B in the y direction. It does not prevent that. Therefore, no force in the y direction. However, the bearing is going to prevent all motion perpendicular to that axis. So all motion in the xz plane is prevented. So we can model that as a component of force along the x direction, I'll call bx, and a component along the z, I'll call bz. I'm assuming positive directions for these so that the equations are just a little bit simpler. But that is taking care of the planar motion xz that is prevented because of the bearing. Now, it's a self-aligned or self-aligning journal bearing, So the self-aligning tells us that that bearing is not going to provide any couples, any moments to the shaft. It allows a little bit of rotation around the Z, the x-axis, and it is going to be a circular shaft through a circular bearing, so it is always able to rotate around that y-axis. So no couples at B, only a BX and a BZ. And for contrast, if it said it was a thrust bearing at B, then that would prevent the translation in the y direction, so there would be a BY. But in this case, nope, just a BX-BZ component. At A, we have a ball and socket joint. So the ball and socket is going to prevent all spatial translation. So we will have an AX, now here we'll have an AY, and we'll have an AZ. Ball and socket does not allow it to move anywhere in space, not along the X, the Y, or the Z axes, so 3 components of force at that ball and socket. The ball and socket does allow rotation, though, at least a little bit, around the X, the Y, and the Z axis. No rotations are prevented, therefore there are not going to be any couples at A. So now our free body diagram is fully marked up. Let's just count. We have 1, 2, 3, 4, 5, 6 unknowns, which again for these sorts of systems is typical. Just because we have 6 doesn't mean we did it right. However, 6 is usually how many we're going to find. So this gives us a little bit of confidence that what we're doing is correct so far. So we're ready to move on to our equations. Looking at all of the forces, everything is acting along a coordinate direction, so no unit vectors are going to be necessary for this problem, so we can move right into solving for some of our forces by starting with summing forces along coordinate directions. So let's start along the x direction. We know it's in static equilibrium, so it's 0. And what do we have in the x direction? We have AX, we have BX, and we have P. And those are the only things with x components. Those are the only forces that will appear in this equation. So we have one equation, we have 3 unknowns. So nothing we can do with it yet, so we can move on. Let's look at the y direction. Sums to 0. We will have an AY, nothing at B, nothing at point D, nothing at C. AY is the only force in the y direction, therefore we'll know, we'll come back to this in the solve step, but therefore AY must be 0. Again, under these loading conditions, AY doesn't need to be anything to prevent translation. So one of our 6 unknowns done. And Z direction, we will have our AZ. We'll have that force from the ball that it's holding, the 150 pounds down. We will have BZ in the Z direction. And that's everything. So we have AZ and BZ. So if we look, we have equations 1 and 3. We really have 2 equations we have not yet used for 5 unknowns. So nothing we can do yet with this. So 3 force equations done. I'll put aside equations 1 to 3, and I'm going to do my moment equation next. So I can take the moment around any point, and I will get the 0 vector. Looking at the free body diagram, I have 3 unknown forces acting through A. Also, A is the origin, so I'm going to recommend let's do the moment around point A. Can do it around any point we want, B, C, D, or whatever. A is just going to be the easiest for us to do. So one reason it's easy, AX, AY, AZ do not contribute to the moment around A. Then looking at the free body diagram, let's look at couples first. Our free body diagram has no couples in it, so all of the moment is going to come from cross products. So we're going to have here a cross product. We'll have RAC cross negative 150K. So that's from that weight, that's from the tension in that rope, is RAC cross negative 150. Plus, we're going to have RAB cross what I'll just call the B vector. This will be BX and BZ inside there. Plus RAD cross P in the I direction. So we can turn these cross products into their determinants next. RAC, because A is the origin, that's just going to mean this is positive 0.5. Let me just make sure that's clear here. Positive 0.5, 2, 0, and then 0, 0, negative 150. We're in base units here. This is feet and this is pounds. RAB is going to be, I have my I, J, and K, 0, 4, 0, feet. And then B is going to be BX in the I direction, 0 in the J, and then BZ in the K. And then finally RAD will be IJK, 0, 6, negative 1, P in the I direction, and then 0 and 0. There's no J component, there's no J, there's no K. And then again, this will be in feet, and then this will come out automatically in pounds because everything will be in base units, and that 150 is in pounds. Now let's expand these determinants. So we're going to have I will have a negative 300 I hat. J is going to give us a minus negative 150 times 0.5, so that's a plus 75J. And then the K is going to be 0 for the first cross product, the first determinant. Moving on to the second determinant, we're going to have a 4BZ in the I hat direction. In the J direction, we're going to have 0. And in the K, we are going to get a minus 4BX. And finally, the third determinant. In the I direction, we'll have 6 times 0 is 0, minus negative 1 times 0, so there's no I term. Then we're going to subtract the J term. We're going to have 0 minus negative P is a positive P, but we're subtracting that, so that comes out negative P in the J direction. So 3 negative signs there that we have to keep track of. And in the K direction, we're going to have 0 minus 6P is negative 6P, and that's in the K direction. And this is the 0 vector, 0 vector. So let's group our like terms. We have negative 300. We have a plus 4BZ, and those are the I hat terms. In the J, we'll have a 75 minus a P. And in the Z direction, we will have, or the K, negative 4BX minus 6P K hat. And now we can write our 3 scalar equations out of this. So I components, I coefficients, 0 on the left is negative 300 plus 4BZ on the right. Equation 5, 0 on the J on the left, 75 minus P on the right is our J coefficients, and K coefficient 0 on the left, negative 4BX minus 6P on the right. So finally, solve. If we look before we get to the solve step, let's count up. We now have 6 equations. Number 2 we've already used, but 6 equations, 1, 2, 3, 4, 5, and 6. And we have 6 unknowns. We have AX, AY, AZ, BX, BZ, and P. So we do have a solvable system before we go on to this solve step. Always important to check that. So let's go about solving some of these. I'm going to start with equation 5. P is my only unknown in it, so I can solve for P. P is going to be 75 pounds. Again, everything was in base units here, so I wasn't really keeping track of units the whole way through. The base units being feet and pounds, that everything was in here. I can move on to 4. BZ is the only thing I don't know in 4. That is also going to be 75 pounds. They both turned out to be positive. They agreed with our assumption. And while I'm down here, I have my equation 6. This uses P, which I already know from equation 5. So BX is the only remaining unknown. BX, I get a little bit around it here, negative 113 pounds. So 3 unknowns solved for. In fact, I have a 4th one. Let me copy down equation 2 told me that AY was 0. Going back up, I have not used equations 1 or 3. At this point, I know BZ, I know BX, and I know P. So let me do equation 3 and solve that for AZ. Knowing what I know from equations 4, 5, and 6, AZ I get also 75 pounds. And finally my equation 1, refreshing one more time up here. I know BX and I know P, so the only thing I don't know now is going to be AX. So my final unknown, AX, I can solve for, and that turns out to be, to 3 digits of precision, 37.5 pounds. So I developed my 6 equilibrium equations, 3 scalar force equations, and then my 1 vector moment equation that I split into 3 scalar equations. I saw that I had 6 equations for my 6 unknowns that were introduced in the free body diagram, and then the solution step was pretty straightforward. Because I chose to take the moment about A, the equations came out pretty simply. The equations 4, 5, and 6 from the moment came out pretty simply, and the solution was very easy to get to by hand.